Right, thus far we have looked at the locus representing the complex number z in the form of a circle. We are very sure of what type of equations will actually give us the locus in the form of a circle. Now the next locus that we are interested in is actually the perpendicular bisector of a line segment. Now the equation that will actually depict such a perpendicular bisector of a line segment is given by as what you see here in this standard form. Now let me explain a little bit more on why this standard form of this equation gives you the perpendicular bisector of a line segment. Now in the equation given in the standard form, z being a variable complex number minus a being one fixed complex number is equals to z minus b, another fixed complex number. Alright, so if I were to represent the points of these complex numbers in an Argand diagram, the complex number z is represented by the point P, the complex number a is represented by the point a cap, right? Z again is represented by the point P, and B, the fixed complex number B is represented by B cap. Alright. So it seems to be saying that from our previous understanding that the distance between P and A is always equal to the distance between P and B. Now if this is so, what will we actually get? Right. So let's take a look at this diagram whether whatever that I've just said makes sense. I have the point A here and I have the point B. Now I want to form a set of points P such that the distance between P and A is always the same. What can I do? Now one way is to use a protector. Alright, you mark a line there and here. Alright, and then from the point A you mark another line here and here, and in that sense you are actually bisecting the line segment A and B, and joining the 2 points that you have created, you actually have this particular line which bisect the line segment A and B in 2 equal parts. Now I am telling you that this line that I've just drawn is actually the locus of the point Z. Would you believe? Okay, let's take a look. Now if I were to choose any point on this line, let's say this point, right, and then I connect it to the point A and connect it to the point B, would you believe that these 2 lines are actually the same distance? How about if I were to choose a point here, the point P here? This is obvious to you because this is indeed the bisected. Right? How about if I were to choose a point here? Again, we realize that these 2 distances are the same. So indeed, alright, this equation that you see here is actually the perpendicular bisector of the line segment joining A and B. Alright, so this is one other locus after the circle that you are going to actually learn about. Okay, let's take a look at example 31a. Now we know that the standard form of the locus of a perpendicular bisector of line segment will take this form. Just as a recap, z minus p1 plus q1i is equals to modulus of z minus p2 plus q2i. Okay, so again the point p represents the variable complex number z, and the point A represents the complex number p1 plus q1i, and the point B represents the complex number p2 plus q2i. So we are saying that the distance between P and A is always equals to the distance between P and B. Alright, so how do we actually form this locus? Okay, so the first step that we need to do is actually to write the equation in the standard form like so. Alright, so this z represent the point P, this one negative 2 plus 3i represent the point, let's say we call it A, and this one is the point B. Okay, so what you need to do in the first place is to mark these 2 points first. So you draw your imaginary axis and the real axis. Right. So negative 2 plus 3. So negative 2, 3 is here. So this point is the point A. And the other one is 1, negative 3. 1 and negative 3. So this is the point B. Right, so you will connect these 2 points to form the line segment AB, and then from there you use your compass. From the point A, you mark 2 lines like so. Then from the point B, you mark another 2 lines, and from there you are actually bisecting this line segment AB, and you can form the line. Right, and you know that this distance is the same, and this is 90 degrees. Right, so the locus of the complex number z is represented by all the points on the line. Okay, so like what we have discussed before, any point on this line, alright, if you were to connect it to the point A and the point B, the distance from A to P and P to B is always the same, and that actually satisfies the equation of this equation. Alright, so some other things to take note of. Alright, you can always find the midpoint joining the line segment A and B. You can also find the gradient of the line segment AB to actually get the gradient of the perpendicular bisector. Alright, which is in this case this value. Okay, so having the gradient of the perpendicular bisector and also having the midpoint, you can always form the equation of the perpendicular bisector. Alright, so I shall not delve too deeply into finding the equation, because you can always use your equation of a straight line to find the equation of this perpendicular bisector. Alright, so maybe just to do a quick recap, you can use y equals to mx plus c, or y minus y1 equals to mx minus x1. Right, now alternatively you could also like what we have done before in finding out the Cartesian form of the equation of the circle, for you to find the Cartesian form of the equation of the perpendicular bisector, you can actually convert the z into the x plus iy form as what you see here, and you can actually get the same result. Okay, let's continue with example 31b. Alright, so like what we have done before, we write the standard form of the equation, and you will be able to get this form. Okay, so we are still looking at the distance between the point P and A, P and B. Right, so let's start to draw. So we have the imaginary, real. Point A is 1, 2, 1, 2. So this is A 1 2. Point B is negative 3 0. Right. So marking those points, you can join the 2 points to form the line segment. Right. So using your compass again, from point A you mark 2 lines. From point B, right, then you bisect the line segment AB. Okay. You know that these two are equal length to each other, and this is 90 degrees. Right. It can be found easily. The midpoint between A and B is this point, negative 1 1, which is here. Right. And you can actually get the gradient of the line segment AB using the two coordinates of the 2 points, which is half, and then you can find the gradient of the perpendicular bisector, and you can form the equation of the perpendicular bisector. Right. As in the previous example, you can also do it in the alternative way, right, by converting the variable complex number in the form of x plus I form, x plus iy form, and simplify it so that you can get the same equation.